Okay, let's unpack this. Welcome to the deep dive.
Glad to be here.
Today, we're going deep into something absolutely fundamental. It's about making AI actually work outside the lab. We're talking the infrastructure it needs to run on.
Yeah, exactly. It's easy to get focused just on the models, the algorithms.
Right, the cool stuff.
But, without the right foundation, the hardware, software, the management tools, none of that really powerful AI actually happens in the real world.
It's like the hidden plumbing, right? The power grid for AI.
Yeah, it's a great way to put it. Understanding this layer, it's crucial. Doesn't matter if you're a developer, an IT pro deploying this stuff,
Yeah.
or, just curious about how AI works at scale.
It really is where the rubber meets the road.
hmm
And our source material for this deep dive, it gives us a really practical angle. We're looking at practice questions for an HPE exam, the HPE2-B08, which is all about AI solutions infrastructure.
Right, so these questions, they basically shine a light on the core technical concepts, what HPE considers essential knowledge, especially using their tech.
They show us the building blocks, the challenges you need to grapple with to actually put AI to work in, like an enterprise environment.
Yeah.
So our mission today is pretty straightforward. We want to pull out those key nuggets of knowledge from these exam points, figure out why they matter.
And connect the dots.
Exactly. Connect the dots to give you a clearer picture of what's needed for solid AI infrastructure. Ready to jump in?
Let's do it.
Okay, part one then. Let's start right at the bottom layer. The physical hardware. AI, especially deep learning. Man, it's compute intensive and data hungry.
Oh, absolutely. And the performance you get, it's so heavily tied to the metal underneath, and importantly, how data moves around.
And the needs aren't always the same, right? Like training a model versus using it for inference.
Totally different demands. Training involves learning from massive data sets, often distributed. Inference is about getting a quick answer from an already trained model.
Okay, so our material picks up on that difference when it talks about storage. For
Okay.
AI inference, it says speed is king. You need results like now.
Yeah, think about fraud detection systems,
Bruh.
or maybe an autonomous car making a decision.
Milliseconds count.
Exactly, milliseconds count, which points directly to storage types that offer the absolute lowest latency.
And the source mentions NVMe SSDs.
NVMe SSDs, yep, that's what it highlights for this exact reason, low latency.
So why NVMe? I mean, compared to older stuff like hard drives or even SATA SSDs, what's the magic?
It's really about the connection.
Yeah.
NVMe talks directly over the PCIe bus. Think of it like a superhighway straight to the processor.
Ah, not the slower SATA route.
Right, so you get dramatically lower latency, much higher speeds. For inference, where that model needs to grab maybe some weights or reference data, super fast.
To give you that quick prediction?
Exactly. NVMe just gets rid of that storage bottleneck.
Yep.
It makes those near real-time responses actually achievable. It's a performance play, definitely.
Okay, so low latency NVMe for speedy inference. Makes sense. Now let's switch gears. AI training. You mentioned it's often distributed, lots of servers working together.
Hmm. Training involves these servers constantly chatting back and forth. They're exchanging updates, parameters, trying to learn together.
So it's not just a little bit of data. It sounds like a flood.
It is. It's a torrent of data, which is why our materials emphasize that for optimal training, you need both high bandwidth and low latency networking.
High bandwidth to handle the volume.
Right, so things don't get clogged up.
And low latency so the data gets there fast.
Precisely. You don't want your expensive GPU sitting idle, just waiting for the next chunk of data. That kills efficiency.
So that's where things like, high-speed Ethernet or InfiniBand come in?
Exactly. Those technologies deliver on both fronts. Lots of data, moving quickly. It makes a huge difference in how fast you can train these complex models.
Okay, so NVMe for inference speed, high bandwidth, low latency networks for training collaboration. The task really dictates the hardware.
It absolutely does.
Yeah.
And this constant push for performance, it leads directly to specialized hardware too.
Your average server maybe can't handle running like dozens of GPUs.
Not really.
Yeah.
Not the density, the power draw, the cooling needed for large-scale training.
Right. Our source points to servers designed specifically for these heavy GPU workloads. It mentions the HPE Apollo 6500.
Yeah, the Apollo 6500 is a prime example. It's engineered from the ground up to pack in multiple high-performance GPUs efficiently.
So it's got the power delivery sorted, the cooling.
All of it. and the right internal connections, the PCIe lanes, to let those GPUs talk to each other and the system effectively. It's purpose-built for that heavy computational lifting that AI demands,
Okay.
way beyond a standard server.
Okay, so that's the foundation. Specialized storage like NVMe, fast networks, GPU-dense servers like the Apollo 6500. That's the physical backbone.
But hardware is just the stage, right?
Mm-hmm.
You need the software, the data processes to actually make it sing, to do the AI magic.
Right. Part 2 then, making the hardware work. The software and data layers. Our materials cover some key things here. First up, something called NVIDIA CUDA.
Ah, CDA. Yeah, it's fundamental. It's a software platform, an API from NVIDIA. It's not hardware itself or a data tool.
Okay, so software, what's its big purpose?
Well, its purpose was pretty revolutionary. It basically unlocked GPUs. It allowed developers to use all those parallel processing cores inside an NVIDIA GPU for general tasks, not just for drawing pictures on a screen.
So it's the bridge between the AI code somebody writes and the actual GPU chip.
That's a perfect way to think about it, yeah. It gives developers the tools, the libraries, to write code that runs across thousands of GPU cores all at once.
And that's what makes AI calculations so much faster on GPUs compared to just using the main processor, the CPU.
Orders of magnitude faster.
Yeah.
It was absolutely critical for the deep learning boom. Frameworks like, TensorFlow or PyTorch, they often use CED underneath it all to communicate with the GPU.
Speaking of data and frameworks, before data even hits the model for training, there's this step mentioned, data preprocessing. Sounds important.
Oh, it's non-negotiable, really. Data almost never comes in perfectly clean and ready to go.
It's messy.
Often, yeah. It can be noisy, missing values, inconsistent formats, maybe structured all wrong for the algorithm.
So preprocessing is like the cleanup crew, making it usable.
It's cleanup, but also transformation. Its main goal is to turn that raw, messy data into a high-quality format that the learning algorithm can actually use effectively.
So things like fixing missing bits, maybe rescaling numbers.
Exactly. Cleaning, scaling, and coding data that's text into numbers, maybe even generating more data like slightly altered images. It's all part of getting the data relevant and ready. You know the saying, garbage in, garbage out?
Yeah.
Well, good pre-processing is how you avoid putting garbage in. It's critical for getting a good, accurate model at the end.
Makes sense. Okay, and then we need the tools to actually build the models. The source talks about AI frameworks and highlights one known for something called dynamic computation graphs. Says it's popular in research.
Ah, right. That's almost certainly PyTorch.
PyTorch, and its key feature is these dynamic graphs. Sounds a bit technical. What does that mean in practice?
Okay, so imagine you're building something complex. Some frameworks, they make you define the entire plan up front. Like, you need the full blueprint before you lay a single brick. That's more like a static graph.
Right.
PyTorch, with its dynamic graph, is more like building as you go. You can make decisions about the next step based on what just happened. The structure can change mid-computation.
Ah, so it's more flexible, interactive.
Much more flexible. This makes it way easier, especially for researchers, to quickly try out new ideas, build weird and wonderful model architectures, and figure out bugs, especially if your data isn't always the same shape or size.
Okay, so we've got the hardware foundation, then CUDA letting us use the GPUs, pre-processing, cleaning the data, and flexible frameworks like PyTorch to build the models. That's a lot of pieces.
It is. And once you have all these pieces, you hit the next challenge. How do you manage and orchestrate this whole complex setup, especially when you scale it up?
Which brings us to part 3, orchestrating and managing everything. And our source brings in some HPE-specific tools here, starting with HPE OneView. What's its main job in an AI context?
The key benefit highlighted is automating the hardware side of things, provisioning and monitoring.
Provisioning, like setting up the servers and storage automatically, taking out the manual work.
Exactly that. Think about an AI environment you might need to spin up new servers, reconfigure networks, or add storage pretty quickly as projects change. OneView automates a lot of that.
So it speeds things up, reduces errors.
Both. Speeds up deployment, makes it more consistent, fewer mistakes from manual setup. It basically gives you centralized, efficient control over that physical layer so the IT folks can focus on more important things.
Okay, then there's HPE Ezmeral. The materials mention 2 key features for AI workload management.
Those are container orchestration and AI lifecycle management.
Okay, container orchestration. That makes me think of Docker, Kubernetes, managing those self-contained software packages.
You got it. Ezmeral leverages containers heavily. Packaging AI apps and all their bits and pieces into containers makes them portable, consistent. Ezmeral provides the tools on top to deploy these containers, manage them, scale them across the cluster efficiently.
Making sure they run reliably.
Right. and utilize the resources well.
And the second part, AI lifecycle management. That sounds bigger.
It is broader. It's about managing the whole AI journey end to end, from getting the data ready, training the model, putting it into production.
And then keeping an eye on it, updating it.
Exactly. Monitoring, retraining, updating over time. Ezmeral aims to provide a single platform to handle all that. Think version control for models and data, tracking experiments, making sure you can reproduce results. It tackles those big operational challenges.
And you mentioned Kubernetes. The source also asks specifically about its role, particularly within HPE Private Cloud AI solutions.
Yeah, Kubernetes has really become the de facto standard for orchestrating containers.
Yeah.
So in an HPE Private Cloud AI context, it's the engine underneath Ezmeral, or working alongside it, that's actually managing those containerized AI applications we talked about.
So it's not providing data or replacing GPUs or acting as a firewall.
Nope, none of that.
Hmm.
Its job is purely managing the deployment, the scaling, the operational health of the containerized AI workloads.
Making sure the apps are running, restarting them if they crash, handling load balancing.
All that crucial operational stuff. It provides the agility and resilience you need to run modern AI applications effectively, whether that's on your own hardware or in some kind of hybrid cloud.
Okay, so it's like layers. One view for the physical metal, Ezmeral managing the AI workloads and their lifecycle using containers, and Kubernetes as the engine orchestrating those containers.
It's definitely a stack.
Yeah.
And you need all those layers working together, which leads to the final piece.
Part 4, accessing AI infrastructure. How do companies actually get all this stuff? Not everyone wants to build and run this whole complex stack themselves, right?
Absolutely not. It's complex, it's expensive up front.
So this is where cloud-like consumption models come in. Our materials mention HPE GreenLake, and it asks about a key advantage for AI cloud deployments.
And the big advantage highlighted is getting that AI infrastructure on demand with a pay-as-you-go model.
So basically, you pay for when you use it, avoids the big upfront cost of buying all the servers and storage.
Precisely. It flips the traditional model of buying everything upfront, capital expenditure, or CapEx. For AI, projects can grow, shrink, change direction really fast.
Yeah, needs can be unpredictable.
Totally. So GreenLake lets organizations start smaller, maybe experiment, and then scale up their resources, compute, storage, whatever, as their AI projects actually take off, without that huge initial investment or the risk of buying too much gear they don't end up needing.
And you get that cloud-like agility, but potentially still running in your own data center.
Or a co-location facility, yeah. It brings the cloud economic model to wherever your workloads need to run. It's about flexibility.
That makes a ton of sense, especially for AI where things change so quickly. We've seen how critical this infrastructure and management stack is today, but AI models themselves are evolving incredibly fast. So the question is, what are the biggest challenges and maybe the biggest opportunities in making sure these foundational layers, the hardware, the software, the management tools, can actually keep pace and evolve just as quickly as the AI they're built to support? Where does the infrastructure need to go next?